welcome everyone to the One World Combinatorics on Words seminar. Our speaker today is Bartek Pawlik from the Silesian University of Technology in Gliwice, Poland, and he's going to speak to us about words avoiding tangrams.
Yes, thank you, Narat, and hello, and thank you for the invitation as well. I'm very pleased to have the opportunity to speak at this seminar again, especially that since it's been a while. I didn't do this intentionally, but over the past few months, due to other commitments, I have been avoiding this seminar. Maybe this is not the best word, avoiding, but as we all know, avoidance is one of the main topics in combinatorics and words. So today's lecture will be precisely about avoidance. And our discussion will be based on the joint work with Gosia Śleszyńska-Nowak, Michał Dębski, and Jarek Gryczuk from Warsaw University of Technology, as well with Kuba Przybyło from AGH University of Krakow. The basics. Yes, if X is the word, then its concatenation with itself is called a square. The examples of squares are presented here. The couscous and the hotshots are such words. And we call the word square free if it does not contain any square factor. Like the word mathematics is square free, but philology is not. And the origins of combinatorics and more date back to 1906 when Axel II proved that it is possible to construct an arbitrarily long a word over a ternary alphabet that avoids squares. And we speak of square avoidance in the sense that no factor forms a square. So factor here is a contiguous subword of a given word. So two constructed a binary word that obviously does not avoid squares because it's impossible for the long binary words, but it avoids overlaps, and then a ternary word that counts the number of ones between consecutive zeros in this word is square free, and this is a very well known and a very elegant construction. Yes. So. What is the tangram? So we know that what the square is, but the tangram is sometimes called an even word, and I believe it was Jarek who first used the term in the context of even words, and it caught on among us while working on the article. So if a given word is a square, then each letter appears an even number of times. And of course, the reverse is not true. A word in which each letter appears an even number of times is not necessarily a square, but we can obtain a square from it by rearranging the order of the letters. And the tangram is an ancient Chinese puzzle, as I think. It's a tale in which all the pieces can be arranged to form a square. So this is why we will call the words in which each letter appears even in number of time tangrams. So of course the word tangram is not a tangram because we have two letters A, but every other letter appears exactly once. And here are 28 tangrams taken from the English dictionary and well from Mathematica, I think, if I remember it correctly. As we already mentioned, the problem of avoiding squares was solved by Thue over 100 years ago, but what about avoiding tangrams? And we know that in long words, tangrams cannot be avoided regardless of the alphabet. To be more precise, every word of length 2 to the power of the number of letters in the alphabet contains a factor that is a tangram. It turns out that this is a simple statement, and I think that the proof of this can be found in Lotter's textbook, but this is a very, very nice proof, so I will go ahead and remind you of it because I like it a lot. Yeah, so basically the proof relies on comparing the binary pairing vectors of the prefixes of a sufficiently long word, and each coordinate of the binary pairing vector of the given word corresponds to one letter of the alphabet and contains the value 0 if the letter appears an even number of times, or the value 1 if the letter appears an odd number of times. And the word of length 2 to the power q has 2 to the power q plus 1 prefixes, including the empty one, yes, and the word itself. But the number of distinct binary pairing vectors of the word over a q element alphabet is 2 to the power q. So it's one less than the number of prefixes. So by this pigeon principle, there must be a pair of prefixes with the same vector. So therefore, if we subtract the shorter prefix from the longer one, we get the word with 0 vector. So it's a tangram, and that's it. That's the whole story about the avoidance of tangrams in the long words. Yeah, so every tangram can be decomposed into factors from which we can create two identical words. And as we remember, this follows not only from the definition of the tangram, but kinda from its name. And if the case of squares, the decomposition is trivial, you simply cut the word in half. And you get two pieces, yes? In the presented example, the chicken was cut right in the middle into two single clocks. So we say that the chicken, the square cockle, has a cutting number 1. And more generally, the cutting number of non-empty tangram is, we say that a word T has a cutting number K, if K is the smallest number of cuts needed to break the word T into pieces. So the number of pieces is K plus 1, from which we can form these two identical words. And the cutting number of word T is denoted by me. And of course, these two resulting words must have the same number of letters, but the number of pieces, these factors used for each of them may differ. So this J is from 1 to K. It's not necessarily in the middle. So if a word is not a tangram, it cannot be split into two identical words. And for convenience, it cannot be split. So for convenience, we assume that in this case, the cutting number is equal to infinity. It was helpful in some proofs, as I recall it correctly. So what are the possible values of the cut number for a tangram? Of course, the cut number must be at least 1. This is the case for Coco and other squares, where a single cut in the middle or on the word is made, and we get the two exact the same pieces. And on the other hand, the cut number cannot exceed the length of the tangram, and in the worst case scenario, is cutting the whole tangram into one letter pieces and then forming squares out of them. By the way, the inequality, this one should to be strict. That's not so important. Okay, so we know how the squares work. So here a couple examples just to show how the definition works. We need to cut this word did twice to get identical words, and this is the minimum number of cuts. We cut in the middle, and we cut between the E and D because we have to rearrange them. So the cutting number of did is 2 because one cut is not sufficient. And if we take the longer word, the situation gets complicated because I can cut it with 3 cuts and show that this turtle tail can be cut into turtle and turtle. But we have to notice that here we just have an creative justification that the cutting number of this word does not exceed 3. From this example, it's not obvious that this number is greater than 2, so you have to check it as well. And in general, determining the cutting number of a given word is a difficult task. So yeah, for these words, these English words from Mathematica, we check the cutting number. It's equal to 1 in the case of squares, equals to 2 for the words of this x, y, y, x pattern, yes. It's 3 for some other words that will tell. And there are 2 words that have cutting number 4, and it's not straightforward to show that it is not 3. You have to check it carefully. So what about the avoidance? Again, we say that the word is k-tangram free if it does not contain factors such that the cutting number is less or equal k. So we can say that word is 1 tangram free if and only if it is square free, yes? And what is the smallest size? The smallest size of the alphabet for which there exists an arbitrarily long k-tangram free word is called the tangram free size, and we denoted it, and it is denoted by tk. So we know that t1 is free, and this is strictly the theorem of Thue, 906. It's because he showed that there are arbitrarily long square free words, so it is sufficient here. And what is a nice thing is that the T2 is free as well, and this is again the same theorem. Theorem of Thue prevents from gives us this result. And why is that? So the little explanation, because it's a nice one. So we can take by the theorem of Thue this long, infinitely long or arbitrary long ternary square free word, and let us assume that t is a tangram factor of this word with cutting number equals to 2. So if the cutting number is 2, then we can split it into 3 pieces for some non-empty factors f1 and f2, f3. And they have to satisfy the certain equation. There are, I think, 6 equations that can be satisfied, but every one of these equations gives us a square. For example, if f1 is f3, f2, yes, like in this case of x, y, y, x, then subtracting f3, f2 for f1, we get this form of tangram t. So here is f2, f2, and this is the square, and this is the contradiction because the word had to be square free. Yes. So in every example here, every possible equation, we get the square. So this theorem of Thue gives us that the list alphabet, which allows us to avoid this tangrams with cutting number 2 is 3. So we have the value of T1, T2. And the next question is, what is the value of T3? And what we did in our article is we get the 2 bounds. The first one is that for every k greater or equal 4, we have this linear bound. We know that tk is not greater than k plus 1 if k is greater or equal 4. So it not necessarily is applying here. And this is this linear bounds comes from 2 facts. First of all, the distance. If I have a word, then the distance between 2 factors is the number of places between the first letter of this factor. So I have this APP factor here and PEIR factor here. So the distance between this A and this P is 2. So this is the distance between these two words. And now I can formulate the de Jonge conjecture, celebrated and well-known de Jonge conjecture, which is in fact a theorem. Now, for every r greater or equal 5, there's an arbitrary wrong word d over the alphabet of size r, such that the distance between two consecutive occurrences f in d is at least r minus 1 f. So what was important for us is one, the de Jonge conjecture. Of course, this conjecture is bigger, but this is the part that is important for us now. And we were able to prove that every factor in the de Jonge word d over the alphabet of the size at least 5 satisfies that the cutting number of s is at least r. So, and this is basically it. We know that the arbitrary long word exists, and we can show that the cutting number of every factor of this word is at least r. So that is sufficient to get this linear bound. And moreover, we have a better estimate, not the linear one, for k big enough. We showed that there is a logarithmic bound. We have t of k less equal than 1024 multiplied by logarithm 2 of k. This is far from optimal because this number is just the convenience. We need to take big enough Zeeman words to get this bound, and the method used was entropy compression. So, as we all know, there are better methods to do such calculations. So, it may be strengthened this result, but we know now that we can go logarithmic with the value of the function t. And from the bottom, the easy fact is that there is logarithm as well, logarithm of 2, and the justification is it's a simple calculation based on we start with the assumption that t of k is less than logarithm, and we get the contradiction with very simple calculations. So this logarithm is very very optimal, I would say. Yes. So now we do have some questions, of course, when we get this bounds. First of all, we know that tk is logarithmic, so we ask ourselves how close it is to the logarithm. And this is the first problem. Is there a constant such that tk is less equal logarithm 2k plus this constant? We would like to know if that's true. And the second question is what is the exact value of t3? Because we know that t1 and t2 equals 3, and this is very easy task. And what's with t3? So now I will show you something that's no longer relevant, actually, but the argument is nice, so why not? I will explain the irrelevance later. So we managed to show that the smallest alphabet size for which the arbitrary long free Tangram free word exists is 4 or 5. The upper bound is straightforward from the de Jonge conjecture in this theorem of ours, theorem 2, this linear bound. And the lower bound, we use the argument that the sufficiently long ternary word contains this palindromic factor, palindromic interior factor. And then we generated the unavoidable Tangram factor, which requires three cuts. So we get the lower bound. The ternary alphabet is not sufficient. How do we get the exact value? We get this linear bound from the de Jong conjecture. So we think that maybe we will look into the de Jong words. And we look at the quaternary de Jong word presented by Jean-Jacques Pension in 1984. But it quickly became clear that this word contains a factor that requires three cuts. So it cannot be an example of quaternary free Tangram free word. Yes? Oh, yeah, this is three cuts. But you see, it might be because it's it turned out that there's a typo in the Pensio work, and we did the sloppy work and didn't check it out, but it was Pascal Ohem who pointed it out. In an email he sent to us a couple of months ago after reading our article. So then we, of course, get excited, thinking that this word might be actually free Tangram free. Yeah, but then somehow we forgot to investigate this thread again. And yeah, but Pascal Ochen didn't. You see, I wrote this current slide a couple of days ago, and it represents my state of knowledge, which I was presenting just an hour ago still. But right before today's talk, I wanted to add some drawing of necklace to these slides, and I carelessly checked my inbox. And instead of preparing to this lecture, I focused my attention on the email that had been waiting for me since yesterday. And Pascal Ohen sent me an article he wrote with Theo Pierron, in which the authors prove that T3 equals 4 and that T4 equals 4 as well. So, as Pascal announced, the paper will soon be on arXiv. So, yeah, so you can soon look it through. And the question about this value of T3 has just become outdated. I didn't even have time to update the slides, but I will do it before I send it to Anna, of course. And I looked at this paper of Pascal's and didn't see anything about this fancy word. So the technique is different from that. So yeah, so this question has an answer, and we don't need to talk about. Oh, we have some on. Oh yeah, yeah, and Pascal send the article to everybody in the chat, so you can read it through. So yeah, very nice work, very nice work. Yes. So the next thing, the abelian case, because we want to. That what we did before with this Tangram free words was to look. We looked at words that looks exactly the same. But what happened if we look at words just to get the pairing vectors right? Now it's the whole new word, so whole different things to go on in here. So I remind you that the word is an abelian square. If it's the form x prime, where the x prime is an anagram of x. So of course, every regular square is an abelian square, as well as some other words like teammate or signings. And again, what is the minimum size of an alphabet such that there exists an arbitrary long word without the abelian squares as factor? This is the question that was posted originally by Paul Erdős, I think in the 60s, in 1961. and was answered by Veikko Keränen in 2005. And Keränen proved that these abelian squares are avoidable on for letters. But there is plenty of nice thing going on. Here, we have this Goldberg-West theorem and the next splitting theorem. The Goldberg-West is that we can put it in the language of combinatorics and word, and it says that for every binary tangram there exist words such that we can split this tangram into words with the same paric vectors, the same number of occurrences of zeros and ones. The theorem is bigger, but this binary case is very easy to prove. You just cut it into half and look at how many zeros is, how many ones is, and you have a match now, or you don't. If you don't, then you just move one position to the right, and if you go to the end, the values will switch here. So somewhere in the middle, they need to be the same. Here, after two steps, they are identical. So yeah, it's going that way. And this necklace splitting theorem, proven by Dr. Alon. Yeah, the every necklace with k times ai bits of color I has k splitting of size at most k minus 1 t, k minus 1 times t, and the number k minus 1 times t is the best possible. And actually, I'm mentioning this because this necklace splitting theorem itself, it's a very nice result with a beautiful topological proof. Was our motivation to investigate this words avoiding tangrams. So we started here, and then we tried to translate it to this non-abelian case. So yeah, this was the start of our investigation here. Yes. And still in the abelian case, there is an open question about this anagram avoidance. So the terminology that is very similar to that which were made in the previous part of the lecture. Alpha t is the least number of cuts needed to decompose a given tangram into factors that can be made into a pair of anagrams. Yes. So the simple facts ABC and ACB, this is not the square, but the value of the function alpha is 1 because ABC and ACB are anagrams. But the tangram AABBCC has to be cut between the A's, B's, and C's as a yes. Here, and here, and this is the least number of cuts. So alpha of this is 3. And again, we have the upper bound is the size of the alphabet because it follows from the splitting necklace theorem. And let k anagram free word be the word that every tangram factor satisfies that alpha is greater than k plus 1. And again, the least size of the alphabet is the ak here. So we know that A1 is 4, and this is this theorem of Keränen of avoiding abelian squares. And there is a conjecture that we posted in our work, but was posted before by Nogalon, Jarek Grybczuk, Michał Nasoń in 2009, that there is this linear bound for every k. ak is less equal k plus 3. Oh. Yes, maybe it is, maybe it's not. We don't have a proof of that. And the last thing here about the avoidance is avoidance of shuffle squares. Shuffle squares is a very, very nice part of combinatorics on words. We like to look at it very intensively lately. So shuffle square is a finite word that can be formed by say shuffling a given word. So if we self shuffle ACA with itself, we can get this ACA ECE. Yeah, and then they are just put two copies of this word in this between. So the formal definition is that the word is shuffle square if we can split the index sets onto two disjoint sets which are monotone, and the letters with corresponding indexes are the same. Yeah, and no, of course, every shuffle square is a tangram, but not every tangram is a shuffle square. Here we have a tangram which is this shuffle square. We can shuffle this word 0, 1, 0 with itself to get this 0, 0, 1, 1, 0, 0. But this is the tangram, but it's not a shuffle square because it needs to start with 0 and then it should be followed by two ones. And here is the 0 at the beginning, here is the 0 at the end. So it is not possible. This is not the shuffle square, and this is a shuffle square. And our binary tangrams with length 6 are shown here, and we pointed out which are not the shuffle squares. 6, 8, 10 of them. 10 of them doesn't satisfy this definition. And so what about avoidance here? What is the size of the alphabet on which we can avoid shuffle squares in arbitrarily long words? So the problem was posted by James Curry in 2014. An unpublished note. It was taken by Miller in his PhD thesis. As I recall, he showed that we can avoid shuffle squares in words of length 10. And then Guéon and Ohem and Pascal Ohem went to the number 7 independently. Gryczuk, Kozik and Bartosz Zalewski did 7 and at the similar time. And it was 2 years ago. We get the better estimation at 6 by Bhutto and co-authors. And we know that it's greater than 3. So as I know, current state of knowledge is that the least size of an alphabet on which we can avoid shuffle squares is 4, 5, and 6. And yeah, that's all for now about the avoidance. And I want to present one more conjecture here. So we say that the words are conjugate if there exist words A and B, such that we can take from the word V the prefix A and put it at the end. And then we have a word B. So they represent the same circular word. We can put it that way. And as we can see, if I take all these 10 binary tangrams of length 6, which are not shuffle squares, then I can take some prefix, put it to the end, and get a shuffle square. Yes. So here we take the prefix 1, 0, put it to the end, and we have the word 1, 1, 1, 0, 1, 0, which is a shuffle square. So I can make all of these words are shuffle squares by putting something at the end. We posted a conjecture that for every binary tangram there exists a shuffle square S such that W and S are conjugate. And we checked this conjecture up to words of length 20. Yeah, and it was investigated by us for some time. We had this partial results that every binary tangram with um, for every binary tangram with for once there exists a shuffle square such that W and S are conjugate. And this is based on this Goldberg-West theorem, this result. Oh, no, sorry, it's not. It's just a simple calculations. It says that you can check it by hand, actually. And this is a simple statement. And this one, this that every binary tangram can be decomposed into two words, such that A and B are conjugate. This is based on the Goldberg-West, and yeah, this is the nice result. But as we can see, there is a counterexample. This conjecture is false, actually. And this counterexample, the smallest counterexample has length 24, and it was obtained by the suggestions of Stepan Holub and Gabriel Fici. I was talking with them about this conjecture in Marseille last year, and they said independently to check some parameter that lead us to the counterexample. So this nice fact is true, but this is not. But this false conjecture can be stated that way, that every binary tangram can be cut into two words A and B such that at least one of two rearrangements of A and B forms a shuffle square. Yes, this 0, 1, 1, 0, 0, 0 is not a shuffle square, but we do this one cut in the middle and we put the prefix at the end, and we get the shuffle square. And now we state the conjecture that every binary tangram can be cut with two cuts into three words ABC, such that at least one of the six possibilities rearrangement forms a shuffle square, because why not? I would say. Maybe it's a crazy conjecture, but this is this counterexample. One cut is not sufficient, so maybe two. And to do a very large conjecture, we stated this one, that every k-nary tangram can be cut with k cuts into k plus 1 words, a1 to ak plus 1, such that at least one of the rearrangements forms a shuffle square. And we do not have any finite bound. We don't know if this never exists. It's possibly not, but this statement looks very similar to the splitting necklace theorem. So yeah, we want to think about it for a while. And I think that this is the moment I will leave you with this, and yeah, thanks for attendance. Thanks for listening.
Thank you very much, Bartek.
Yeah.
Let's see. There's some questions. Hajime.
Thank you for nice talk. So I have a question about the definition of tangram. So you said that the definition of tangram, every letter occurs an even number of times.
Yes, it's an even word. Yes.
Yes, my interest is that, so for example, every letter occurs a number with multiple of 3. That it's an analogy of cubic.
Yes.
So is it possible to consider such an analogy? It's an analogy of cubic 3.
Oh, yes, of course. This is the one way to generalize a whole concept with this Tangram free words. But we haven't looked at it, but I believe that there is plenty of things to do with cube free words and four free words and then the higher powers. Yes, that's. I don't have any any results in that directions, but I think that it could be interesting. Yes.
Okay, thank you.
Are there any other questions for Bartek? No, well, it was a very nice talk, and I am going to read your paper. Yours and Pascal's also. So thanks for telling us about Pascal's result as well. I will
Yes,
definitely.
I was very surprised by this email, and I'm very happy when I saw it because now I can sleep better because I know the truth about the T3 number. So it's very
Right.
nice. Yes.
So that resolves the value of t for k up to 4, right?
Yes, T1 and T2 is theorem of Thue, and T3 and T4 is obtained by Pascal and by Theo.
Okay, and higher than that, it's still open.
The exact value, yes, yes.
Okay, great. All right. Well, if there's nothing else, thank you so much again for your talk.
Thank you.
Thank you everyone for coming today, and we'll see you again in 2 weeks.